Yes, welcome everybody. Today we are going to talk about large language models, opportunities and challenges for the social sciences. And this is a talk part of the Meet the Expert series of GESI's online talks. My name is Dimitar Dimitrov. I am leading the team Information Extraction and Linking. My research interests are in data science, natural language processing, and discourse analysis.
Hello everyone, I'm Hajira and I'm leading team Big Data and Analytics at KTS, and my research interests are data science, knowledge graphs, NLP, and scalable computing.
Okay, now the agenda for today. We will start by looking at the data that we have in social sciences and at GESIS. Then we will have a section on the large language model, looking at definitions, some background and opportunities and challenges. After that, we will show you a small case study on tweet topic relevance. And the last part of the talk will be about adopting LLMs in GESIS services. Yeah. What kind of data do we have at GESIS and also in the social sciences? We have, of course, survey data. And if you're sitting in this talk, you should be familiar with that. We have, however, digital behavior data. These you can think of digital behavior data as posts or interactions with posts on social media. And we have, of course, scholarly data. These are social scientific publications and the associated metadata with that. Yeah, what's common is that this data is basically textual data, a lot of textual data. And on the next couple of slides, I would like to show you how we use natural language processing methods to work with this data and to answer social scientific questions. Let's start with the survey data. The problem that we have here is that surveys are costly, so finding and reusing survey questions and items is very important task. So we would like to really link semantically related questions and responses across survey programs. And on the right, you see an example. So given a question from Albus 2018, we would like to annotate that automatically according to a taxonomy that you see here. And we developed a method to do this. The next data type that we have is digital behavior data, where we would like to enrich online discourse analysis. So discourse data, the problem that we have is that this data can be sensitive, and sometimes platforms prohibit, for example, sharing raw data, in particular Twitter or X. So the task that we identified is creating data sets to facilitate privacy-aware social science research without the need to access raw tweets data. We've been doing that, and there are a couple of example data sets that we annotated using NLP methods, and on the right is an example of how we annotate geotagged tweets from COVID-19 discourse on Twitter. And there will be a Meet the Experts talk on this topic if you're interested. Now, the third data type is scholarly data, and the problem that we have here is that there is a lack of explicit linking between individual survey variables and publications, which limits, for example, aggregate analysis. And the task that we have identified is really to identify relevant variables from English and German social science publications, given a set of variables and sentences, as you see on the right. So we developed a method, and we have a publication on this method and a demo. If you like, you could check it out. And if you're interested in this topic, there will be another talk on introduction to scholarly information extraction. Yeah, so these were just 3 examples of NLP methods that help us in the social sciences, but there are many more, as you can see on this slide. And they can be very helpful to solve or to address research problems in social sciences. However, creating these methods can be very expensive because they require ground truth data to train them, and very often we need to develop them from scratch. And in the next part of the talk, we will see how we can use LLMs to address these challenges. Yeah, so let's start with the definition. What is a language model? Language model aims to model the generative likelihood of a word sequence as to predict the probability of a future or missing tokens. So to give you an example, let's say we have an input, Dante was born in question mark, and we have a model that we can prompt with this input, and the model basically generates this distribution for possible words that we can fill here. And we see that in this example, Rom has the highest probability, and this is what actually the model's output. So the model generates the word Rom. Now, there is a definition that I found on large language models that will serve the purpose for this talk. And yeah, large generative purpose language models yeah, are pre-trained and can be fine-tuned for specific tasks. So let's break down this definition on the next couple of slides. Pre-training, yeah, LLMs are pre-trained to solve common language tasks like predicting the next or missing token. And we do that in a self-supervised manner using large amounts of cheap textual data. The learning is done using the transformer architecture and neural networks. Yeah, what do we get at the end? So we have at the end we have these word representations, basically vectors that capture the distributional semantics of words in a language. And on the right, you see an example. We have for the word shark, a vector that is closer to the vector of animal and closer to dangerous. And at the same time, it's a bit far away from dictatorship, for example. Yeah, so these word representations or these vectors are very useful because they're transferable and can be easily reused for domain-specific tasks, for example, or models. Fine-tuning, the other keyword in the definition. Fine-tuning is basically retraining a model to better solve domain-specific tasks. This could be, for example, political leaning detection. And on the right, you see a picture that shows this process of fine-tuning, where we basically build upon a pre-trained model. We need, yeah, we do the fine-tuning using, yeah, supervised learning, and we require a small field data set, like several hundred training examples, often that are often expensive to obtain, and you need crowd workers or domain experts to generate this ground truth. And then at the end of this process, you get this fine-tuned model that can solve this task of political leaning detection, for example, very good. Now, to the last keyword that I would like to show you is, yeah, which is large. So this word basically refers to a couple of aspects here. The first one is the amount of data on which the model has been pre-trained. Then we have the number of parameters of the model that basically captures how powerful the model is. The third aspect is the dictionary size. This is basically the number of words known to the model. And the instruction set size, these are the number of user prompt model output pairs to create this chat functionality, basically. And this keyword also refers to, yeah, to the ability of the model to understand natural language, which is in the case of the large language model very high. And with that, we go to the next section of the talk, where we'll talk about the opportunities. Yeah, this high level of natural language understanding of the model can help us to solve common language problems in social sciences, like text generation, text classification. We could, for example, annotate tweets with those models, or we could do document summarization, which can be useful, for example, to summarize results page of a search engine. this high level of human natural language understanding also is also very exciting because it offers this zero-shot prompting scenario, which is basically means that the model can recognize concepts that have not been explicitly taught in the training phase. And you see here on the right an example where we ask the model to classify a sentence in conservative or liberal, and this is what we get actually out of the model. And yeah, this is exciting because we don't need additional data to accomplish this task compared to the fine-tuning scenario that I showed you, and also compared to this few-shot prompting scenario where we would again ask the model, but provide also a couple of training examples. Yeah, later on in the talk, I will show you a case study with zero-shot prompting. Now to the advantages that we have with large language models. So they are very easy to use. So no technical skills are needed to prompt a model. They are very easy to reuse. A single model can be used for different tasks, and a fine-tuning requires only small field data set. LLMs are less expensive than humans, so zero-shot prompting and few-shot prompting requires no or minimal amount of label training data. And yeah, large language models are very specific. You can apply them to different tasks, but if we think of, let's say, data annotation, yeah, you could, for example, provide different labels, categories, or output schema on the fly. Now on this slide, I would like to, make the opportunities once more that we see once more explicit and relate them to the methods that I showed you in the beginning from the different that we could develop and are useful for the social sciences. So the first opportunity that we see is related to prompting. So we could directly apply zero-shot and few-shot prompting to enrich social science data. We could use zero-shot prompting to create ground truth data for training NLP models. So the opportunity that we see here is cost-efficient data annotation and ground truth data creation. So that's the one side. The other side is related to training. Yeah, we could, for example, pre-train LLMs on social science data like Twitter data or Telegram data, or we could fine-tune LLMs with domain-specific data, for example, political leaning or stance detection. So the opportunity that we see is that we will have better methods through better foundational models, and we would not need to start from scratch when we develop an NLP method. Okay, yeah, and now if we have a look at the methods that I showed you in the beginning, now you see that some of them are marked in blue, and these are basically the methods that we develop here at KTS and GESIS, and that are already benefiting from the opportunities that I just showed you. Now I would like to hand over to Hajira for the next part of the talk.
So on one hand, we have seen these interesting opportunities and applications that can be explored with LLMs, and the fact that LLMs are so good with generating text that they can give a false impression that they are intelligent enough. On the other hand, however, LLMs do pose certain challenges while being used, and this is what we are going to cover in this section. So large language models are known to be trained on very large volumes of text. While they might demonstrate satisfactory performance in the beginning, they may experience a decline in their performance or predictive ability over time. And this could be due to one of the two reasons. First is data drift, where the data evolves with time, potentially introducing previously unseen data. For example, new knowledge emerges over time, like there are new presidents, wars, or other events can happen. Concept drift is that our interpretation of the data changes over time, which usually then requires relabeling of this data. In both cases, the performance of model decays over time due to this drift. And this could affect the downstream annotation tasks like sentiment analysis, opinion mining, or stance detection. So another challenge is robustness. So robustness in LLMs refers to their ability to maintain accurate and coherent responses across various inputs and scenarios. However, in practice, small changes in prompts, like syntactical changes using synonyms or even small typos, can lead to very different results. For example, in one of our ongoing work, we are exploring the biases towards certain syntax types. In the given example, we see that Dante was born in, and we have a blank which is filled by a Rome with the highest probability. When we slightly rephrase the sentence with dash is a place where, and Dante was born here, the highest probability moves from Rome to it. And similarly, another rephrasing gives us this as a word with highest probability. So lack of robustness in LLMs can stem from different factors. For example, LLMs are trained on big collections of text from the internet, and it can end up favoring dominant linguistic styles and perceptions. Or they might exhibit biases present in the training data they utilize, affecting marginalized or specialized tasks. Furthermore, LLMs also lack the contextual understanding as we observed in this given example, and this could result in different answers when given minimal changes. So the risk that we have here is that minimal changes impact downstream tasks substantially. For example, meaningless text generation or wrong or unreliable classification. So hallucination is when an LLM generates a response that appears grammatically correct, but is in fact incorrect, nonsensical, or disconnected from the input prompt. This misleading information can range from minor factual errors to completely fabricated knowledge. Sometimes this novelty is also desirable for tasks like novel writing and so on. Why hallucination exists is not really known. There can be several contributing factors, such as limitations or quality of training data, biases in the model, or inherent complexity of language itself. LLMs may try to generalize from data without being able to verify its accuracy when asked about unseen topics. The risks of hallucination are if we use LLMs for decision making, we could get fabricated information on undesired output. This leads to mistrust in LLMs as they return misleading information. LLMs can likely exhibit the cognitive biases found in their training data from the internet as well, and this could result in ethical concerns and discriminating content as its output. Therefore, LLMs must be used with caution. In order to handle legal and privacy issues, currently no regulations about the use of generative AI or large language models are substantially materialized. Most of the time, commercial LLMs are known to be trained on data based on information scraped from internet without permissions, and probably in violation of intellectual property rights. They might be trained on non-GDPR conform and copyright protected data. In terms of privacy, LLMs can leak their training data, which might be personal data, and LLMs can be explicitly attacked as well to extract the training data. The risks here are that LLM can output illegal suggestions or simply suggest something that results in copyright or intellectual property right issues, exposing their users to potential legal liabilities. Users might be using proprietary information leaked through LLMs unknowingly. So mostly these challenges can be mitigated through introducing culture and diversity in training data and development teams. For output, conducting regular performance audits, looking into the corner cases, and benchmarking the output and performance is usually conducted. There are tools for LLM operations or LLM ops in short to do the performance monitoring and auditing of LLMs. These could also be used to monitor the performance decay and help to detect cause and to determine when to retrain the model or when to relabel the data for retraining. Legal issues can be mitigated through making the training data and its biases more transparent, as well as the output monitoring. Other risk mitigation techniques use controlled output generation. There we have retrieval augmented generation, It works by extracting or authenticating information from a given external database. Another method is chain of thought prompting that uses the prompt simulating human reasoning or thinking process to conclude the output. And furthermore, adding transparency or explainability to the results could also help us. However, it should be noted that in case of commercial LLMs like GPT, we do not have access to either the training data or the model itself to retrain it. Now I hand
Okay.
over to Dean.
Yes, thank you. Yeah, as promised, I would like to show you a case study on tweet topic relevance. And yeah, so it's about this case study is about understanding the tweet relevance to a specific topic. And given a tweet, an LLM should assign a score to indicate how relevant the tweet is with respect to a given topic. And for this case study, we selected the topic environment. We asked 3 human annotators to assign relevance scores to 100 tweets. And we used ChatGPT in this zero-shot prompting setup that I mentioned to perform the study. Yeah, and this is an ongoing work by Felix Bensman and Debanjali Biswas. Yeah, now to zero-shot prompting. How did we do that? We basically provided the exactly same extraction to the model as we did to the human annotators. And then in a second step, we provided a set of tweets to the model. And what we got as output looks like this. So we have for each tweet a relevance score assigned. And now the question for us is, okay, how well did the model do? On this slide, I would like to show you the results. So what we see here is a table. The first column contains the inter-annotator agreement of our 3 human annotators. The second row contains the inter-annotator agreement between the human annotators and the model. And the last row shows you the difference. And we see that for different relevance cutoffs. To calculate inter-annotator agreement, we used the Flies kappa measure here. And what we observe is that the absolute difference is less than 0.07. This suggests that the model did very well to comparable to humans with this annotation task. And this can be very useful for such data annotation tasks that can be then later on used in natural language processing methods for the social sciences. Now, moving to the next part, this case study is actually very nice and is relevant to the service that I would like to show you. First, this is the web data for the social sciences services, where we basically collect digital behavior data, in particular from social media. And we've been doing this for already more than 10 years for Twitter, for example, or X. And based on this raw data, we create different data offers. We basically use NLP methods to annotate this corpora. And one example is Tweets KB, but we also have Tweets COF19 and the Bundestag or German parliament election data sets that are annotated using traditional methods. But now we could use, of course, directly apply, for example, zero-shot learning or zero-shot prompting to enrich social media data. For example, apply this tweet relevance score method. And we could also use a zero-shot and few-shot to create ground truth data for training NLP methods like political leaning detection. Now I would hand over back to Hajira for the next part. Oh, yeah, I forgot something to say, that we are actually collecting data also from additional platforms like Telegram and TikTok.
Thanks, Timmy. So another service that we are working on is Methods Hub. It is a repository of computational methods for social science applications. In this repository, we have a gallery of methods that perform different tasks like data collection, ranging from data collection to data analysis. We have execution environment that offers reusability and reproducibility of these methods, and tutorials enabling social scientists to use these methods for own digital data and for your own research questions. Methods Hub act as a central point to address LLM opportunities and challenges as well. Methods Hub shows how to apply large language models for own research or different research questions. It bundles large language models and methods for tasks like claim detection, stance detection, and it offers use of social science specific large language models like using German Tweetsbird pre-trained on German Twitter data for tasks like detecting relevant entities in the given piece of text or detecting sentiments against these entities in text. Please note that this is a service that we are working on at the moment, and it will be made publicly available next year. Another service that we've been working on is GACE's Research Knowledge Graph. So up till now, we have seen different types of data, different methods that can use LLMs and applied on these different data types, resulting in data sets, publications on one hand, and claims, topics, entities, or sentiments on the other hand. GACE's knowledge graph interlinks these resources and concepts to show, for example, which method has been applied to which data set, or which entities belong to which publications, and so on. This GACE's knowledge graph, containing all of this information, empowers our GACE's search. So in GACE's search, for example, if you search for a keyword migration, on one hand, you get a list of research answers, but on the right hand, you also see other resources relevant to your keyword. Migration. Yeah. So on right hand, you can see that we have data sets, other resources that can be downloaded or that are connected to your keyword migration. So in summary, in this presentation, we have seen that textual data and NLP methods are omnipresent in social science and at GACE's. The opportunities from LLMs are that they give us cost-efficient data annotation and ground truth generation capabilities. They offer better performance through better foundational models. The challenge here is that LLMs lack robustness, suffer from performance decay, hallucination, and they give us legal or privacy issues as well. LLMs are already being adopted in many services at GACE's. So here I would like to highlight that there are a few upcoming talks, for example, preserving and analyzing large-scale Twitter data or introduction to scholarly information extraction. Kindly visit our website to get more information about upcoming talks. Finally, we have our service, VIP Data, needs your input. Please use this QR code to fill the survey where we want to better understand your data needs and we want to work towards collection of this data. Thank you very much.